So we've talked a lot about disorder in the last 6 days. So today I want to talk about non-crystalline media, metal insulator transition in metallic polymers, and subjects related to that. So let's just remind ourselves, in a good crystal, okay, or in a very perfect polymer chain that is all straight and fully extended, you have translational symmetry, translational invariance. And because you have translational invariance, you can express, and you, in a sense, you must express the energy levels of the system in K-space, okay? Instead of, and you know this, and so the energy of a, here's the energy band of a metal, idealized picture, E of K versus K. It looks like free electrons down here. These are the occupied states. These are the unoccupied states. K, which is 2 pi over the over lambda, 2 pi over the wavelength, and h bar k is the momentum. K is the good quantum number. And of course, you look at the density of states, all of these states are filled, so these states are filled, all of these states are empty, but all of these states are fully delocalized over the structure. In a metal, one way to look at a metal is that you have a Fermi C. If you put on an electric field, you displace that Fermi C. Electrons are moving. What's the mean free path of an electron? You write the conductivity. And the mobility mu is E tau over the mass, and tau is the scattering time. So the mean free path, let's call it L, is the Fermi velocity times the scattering time tau. Okay. And if you play this game, if you take the electrical conductivity of copper and take the number of electrons per unit volume of copper, both of which are, very simple, there's 1 electron per atom, you know the density, you'll calculate the tau, and we know the Fermi velocity is something a few times 10 to the 8th, but the answer comes out to be about 150 angstroms at room temperature in copper. Now the lattice constant of copper, is approximately 2 angstroms. So here we are at room temperature, and in copper the mean free path is of course much greater than the lattice constant. Because the mean free path is much greater than the lattice constant, the momentum of the electrons is very well defined. K is very well defined, right? So if K is very well defined, then you can draw a curve you can draw curves of this kind, and they're meaningful. Okay, the energy versus K is meaningful. So what happens then when you start to turn on imperfections? Well, I just told you, if you have copper as a metal, and you turn on thermal motion, thermal disorder because of phonons, then at room temperature it's not so serious. Okay? At room temperature, conductivity is still high, the mean free path is still very large. So even though there's a lot of thermal motion in a metal like copper at room temperature, the states are very well defined. Mean free path is much greater than the lattice constant, and the system is still metallic copper. Suppose, however, you have stronger scattering. So suppose the uncertainty in K becomes comparable to its magnitude, then it's very easy to write this down. That means that in the same analogy that I made there, the Fermi momentum, Kf, times the mean free path is approximately 1. If KFL is less than 1, then you can't even talk about the wave of that entity, of that electron, of that electronic state. And this was pointed out a long time ago by Joffe and Regel, and it's called the Joffe-Regel limit. And the argument is that if the mean free path becomes shorter than something like a lattice constant, you cannot have a metal anymore. Or saying it even more generally, the states are not well defined. Now, what happens, people speculated on this, but what happens when the disorder becomes greater than, when the disorder becomes so large that KFL would be less than 1, we now know, because of the work of Anderson in 1958 and the work of others, that the wave functions become localized. They're no longer extended waves. They become localized, and this localization length, 1 over A, will depend on the strength of the disorder. And there's an interesting point here, right, that in a very strong limit where you have localized states, in this kind of a model, okay, the question is what happens, okay? So let's just imagine I put in disorder with an average value, a random potential on every site, a random potential on every site, but the average is still 0, okay? Then the average energy of all the states is not going to change. You'll get a little bit, you'll get some band tailing. That typically happens. You get some band tailing out like this, and this all becomes somewhat more smooth schematically. You still have, in this case, you still have the same number of electrons. The number of electrons is determined by the area under this curve, right? This is the density of states, and if you integrate the density of states, you get the number of electrons. The number of electrons doesn't change if you put in a little bit of disorder, even a lot of disorder. But what happens is, gradually, as you increase the strength of the disorder, these states get localized. And these states get localized. If you make the disorder bigger, disorder potential bigger, and if you make it still bigger, so as the disorder increases, states from the band edge get more, farther and farther into the band, become localized in the sense that I've described here. And in the absolute limit, where the disorder is very large, all those states are localized. But the exclusion principle is still valid, so you can't have more than 1 electron in a state, so there's still a Fermi energy. There's no energy gap, but all the states are localized. All these are occupied. All these are empty. So this is still a continuum of states, but since all the states are localized, it's not a metal. What Anderson called it is a Fermi glass. Because it is a system of fermions that is highly disordered. All the electrons, of course, obey Fermi statistics. So there's no energy gap here. There's an absolute continuum. All these states are still here. There's a sharp cutoff in the occupation number at the Fermi energy. There is no energy gap, but it's still an insulator. It's an insulator because all the states are localized. And I guess that's the picture that I'm showing you here. So Fermi glass is what you get in the limit, if you take a metal and you increase the disorder to the point where all the states are localized. Okay? And I've said that here, you know, in the Fermi glass limit, the conductivity goes to 0 because the mobility goes to 0. There are plenty of carriers around. That is to say, all these electrons that are in this half-filled band in this model, in principle, could contribute to it, and they do in the pure material, but now they're all in localized states. So the electrical conductivity goes to 0, even though the density of states is not 0. The only way you can get electrical conductivity in a system like this is for electrons in a state here to thermally hop to another state, a different energy, and in real space to hop phonon-assisted hopping. So this is what I said a moment ago. If you imagine a perfect lattice where you have the same potential at every site, you know, then you get a nice, very well defined energy band. If you put on if you put on disorder, that disorder could be thermal, so that it would not be static, or it could be impurities, or it could be, you know, take a piece of copper and cold work it. I mean, so you just put in a lot of defects. What happens is then that these states become less well defined, you get band tailing, et cetera, et cetera. So here's a simple model, okay, where we talk about site diagonal disorder. That is, every site has some randomness to the energy. And let's call that randomness 1/2. Let's make that be 1/2 V0. And what happens as you increase the strength of the disorder? It's exactly as I was describing. This is work from Anderson and Mott and many others, but there's a concept here that I want to introduce. So as you increase the size of the disorder, starting at the band edges, these states become localized. Okay? This energy right here, which separates the localized from the delocalized states, called by Mott the mobility edge. Okay? It's not, there's not an energy gap there, but the nature of the states changes as you cross the mobility edge. These are localized, these are delocalized. They're not plane waves. You know, if you start off with a simple model of a metal and you make plane waves, or even if you block states, et cetera, they're uniform everywhere, amplitude, but now it's much more complicated, but these are still fully delocalized. So as the potential increases, this mobility edge moves toward from both sides, moves towards the center of the gap, the center of the band, in every band. Okay? And if the band is, if you start off with copper or something like a very broadband system, then, you know, this may not be very important. But if you start off with a single crystal of C60, what is it, potassium 3C60, which is a metal, but there's a very narrow band, then a little bit of disorder immediately will start to come in toward the center. And the critical issue, obviously, is in this picture here, are the states right at the Fermi level localized or not? The states at the Fermi level are localized and nothing can move. Okay? If the mobility edge is down here and the Fermi level is here, then you have localized states, but right near the Fermi level, the states are delocalized and the system would still conduct. You might wonder, can I have localized states and delocalized states at the same energy? And the answer is no. One of the important theorems that Mott proved is this: if at some energy there are localized states, then all the states at that energy are localized. The kind of analogy that people make is, so here we are in in this mountainous area with these deep valleys. Let's suppose we had a great flood, okay? Let's suppose we had a, 40 days and 40 nights of heavy rain, and we had a great flood. First, you would have small lakes, and you could get in your little boat and you could go around the lakes. But you couldn't go from here over to there because there's still a big mountain. And then as the water rises and gets above the level of the pass, then you can take your boat and you can go everywhere, okay? Of course, there are still mountains sticking up above you, but there are delocalized states. You can go everywhere. So in a Fermi glass, the mobility edge is, as I said, the Fermi level is a region of localized states. If that's true, then the only way you can get conductivity is by thermal activation, and I'll tell you a little bit about that in a minute. But let's just look qualitatively at what you would expect. So if you have a metal, then as you go to higher and higher temperatures, the resistance goes up because you're scattering more. Okay? If the mobility edge is such that the Fermi level is in localized states, then you must do thermal activation from the Fermi level up to the mobility edge in order to get electrons to move. Okay? So as the mobility edge moves toward the Fermi level, these slopes get less and less. Finally, it becomes a metal, and then you get metallic-like resistivity. So as a rough picture, when you're in the insulator regime, the resistance goes up as you go down in temperature. In the metallic regime, the resistance goes down as you go down in temperature. And that's happening here not because there's an energy gap, but because the states, because they're localization of states. Okay, so if in this example, if the Fermi level were here, then you would have to you'd have to have activation of electrons above the mobility edge in order to get conductivity. If the Fermi level's here, all these states are empty. But even if you thermally activate into those states, they're localized states, so nothing can move. So you have to come up above the mobility edge. Now there is a more clever way to do that, which is called variable range hopping, and I'll tell you about that in a minute. It's slightly more complicated. In this very important paper in 1979, a group of 4 people, including Anderson's, proved that the metal insulator transition due to disorder is a true phase transition, like melting of, like a ferromagnetic paramagnetic transition, or the melting of water, melting of glass, of ice, etc. It's a true phase transition. You go from a metal to a Fermi glass in the way that I just described, and the way that happens, if you think of a moving picture, as the disorder increases, the mobility edge moves in, and eventually you have a Fermi glass, and that is a phase transition. One of the things that you would be interested in the context of that phase transition is how the conductivity goes, how the conductivity increases as a function of the disorder, and the answer is sketched here. I mean, roughly speaking, starts off at a relatively high value at t equals 0. This, by the way, is a quantum phase transition. It's particularly interesting. The metal insulator transition is a quantum phase transition. Happens at t equals 0. It's not a statistical physics problem. It's a quantum mechanics problem. So if you imagine being at very low temperatures, in a metal, of course, the conductivity remains finite, in fact, quite high, limited by the residual resistivity. But as you put in more and more disorder, the conductivity drops. When you get localization and the formation of a Fermi glass, the conductivity goes to 0. Okay, now what happens to that system at finite temperatures, where you are in a Fermi glass regime or highly localized regime, but you have phonons, okay? In a metal, the phonons scatter the electrons, reduce the mean free path, and increase the resistivity. In a metal, phonon scattering decreases the conductivity, increases the resistivity, right? Once you go into the insulating regime, you don't have any mean free path. Everything is localized. So now the phonons enable electrons to get out of this state and move to another state. If you have a situation of the kind that I talked about first, so there are two limits here. Let's talk about two different cases. First case I want to talk about is a very simple one, where the density of states looks like this. Let's say I've got a Fermi level here. All these states are filled, and that determines how many electrons I have. I've got a mobility edge here. All of these states below the mobility edge are localized. Only these are occupied. Okay? So then it's pretty easy to make the argument that if you excite an electron from here up to here, you can get conductivity, and that's the expression that I was writing before. And that's fine. That conductivity will go to zero exponentially as the temperature decreases. Neville Mott, in 1970, I think, invented a different idea. Okay, he called it variable range hopping. All of these states are localized. Okay. But they're localized at different places in the solid. Okay? I want to redraw this picture in another way. Let's just draw this picture in terms of a classic energy band. Okay? And I'm going to say, here's the Fermi level. Here's the bottom of the band. Here's the top of the band. Here's the Fermi. All these states are occupied. Okay? So all these states are occupied. I'm in the Fermi glass limit. All states are occupied, and all states are localized. So, and of course, this is supposed to be here in a diagram like this, X, as I move through the solid, right? So I've got this piece of, I've got this piece of disordered metal, and I'm looking at where the states are in various places in the material. Okay. So I've got a localized state. Everywhere has, all the states are localized. That means they have a finite extent in real space. So there's a state here, it's localized. There's a state here that's localized. There's one here, there's one here, there's one here, there's one here, there's one here. There's one everywhere, okay? And I'm being very schematic. All these states are localized. And the mean spacing between the states is the same as it was. I mean, it's basically the system, the density of states is essentially continuous. It's just that all the states are localized. Now, all these states below the Fermi energy are doubly occupied. All these up here are empty. So now I go to a finite temperature, and Mott observed, if you go to a finite temperature, of course, Mott says, well, look, I can do thermal activation up to here. I can do thermal activation, but I can access this state more easily. It's a smaller activation energy, but it's farther away. Okay? And if you think about that for a moment, it's always true. You have a continuous density of states. They're all localized. If you go far enough away, you're going to find a state here that's infinitesimally close to the Fermi energy. So if you go far enough away, you'll find a state with zero activation energy. But the wave functions are localized. Okay? All these wave functions are localized. So in order to go from here to here, you have to have an overlap of the wave functions, and this is now going to be exponentially small. Okay? So you have this compromise. Thermal activation is easier if you go far away, but to get there, you've got to have overlap of the wave functions, and that means the probability is smaller. So you say then that the probability of hopping is exponent to a hopping from here to here is exponentially small on the distance, but the activation energy is lower if you go out far enough to find a state right near the Fermi energy. So here's the probability of hopping, and it has two features in it. The exponential tail of the tunneling and the hopping energy. And now let's put in an electric field to the right, and that's going to bias the hopping. So now you write the current. If this is the probability of the hopping, then how many electrons can hop? If they do hop, they go a distance r with this probability, and you end up then with an expression that looks like this, which is for small electric field. The hyperbolic sign is proportional to the field, and it begins to look like sigma is equal to NE mu. But there's this interesting problem that the conductivity here has in it this range and this activation energy. Okay, now the hopping energy, as I said, depends on how far the carrier is willing to hop. If you're not going to go very far, you're going to have a big energy. If you're willing to go way out here, you'll find a very small energy. So this energy, on average, goes like 1 over the density of states times a volume, that volume R. If you cut out a volume R, then and you know the density of states, then you're going to find the probability of finding a state at W. If you go out far enough in R, this will get smaller and smaller and smaller. So then Mott realized that you could write then an average hopping distance. And when you write this average hopping distance, you have R bar here, and you also have it in the W. And then you say, or he said, let me maximize the probability. So I take this expression, I take the partial of the derivative with respect to R and set it equal to 0. That tells you a relationship between this alpha and this R, and you find then that the typical hopping distance, if you like, comes from this equation. There's some optimum hopping distance, which depends, you see here, on the temperature. And when you're finished, you get this bizarre expression, which tells you that the electrical conductivity has some nice things in front that you recognize. It goes like the electric charge squared, it has the density of states, has this mean hopping distance squared. It's phonon assisted, so phonon's frequency comes out in front. But the temperature dependence here is this bizarre e to the minus T naught over T to the 1/4. And indeed, in his first paper, Mott took data from many different systems that were available at that time, not so many, but many more now, and he made this plot of the log of the conductivity versus the 1/4 power of 1 over t, and you find a straight line. Okay, this is not a functional dependence you could ever guess. It's just too weird, right? Now remember, in 1971, some of you probably weren't born in 1971. I was at the conference when it was in France, actually, and when Mott first showed this analysis. I just couldn't believe t to the 1/4, right? But it's right. Now, if you look back at the calculation, this 1/4 comes right from here, because I assume 3 dimensions. Okay, this is 4 pi over 3 r cubed is the volume of a sphere in 3 dimensions. If I did this in 2 dimensions, this would be 2 pi r, it would be the area of a disk. And if I did it in 1 dimension, it would be r, just the length of a line. And what you're doing here is taking the derivative with respect to r. So if you have r cubed here, you know 1 over r to the minus 3 goes to r minus 4. R to the minus 2 goes to r. So the answer then is at the bottom here. If you do this in 3 dimensions, you get 1/4. If you do it in 2 dimensions, so the answer that you get more generally, I don't think you can read that, is 1 over d plus 1. Okay, so if dimensionality is 3, then this is 1/4, 2 it's 1/2, 1/3, and 1 is 1/2. So now we have a mechanism for electrical conductivity if I have localized states. Okay? And I went through all of that because I have to understand, I do experiments at real temperatures, not at t equals 0. Metal insulator transition is a 0 temperature phase transition, and I'm going to show you that that one can study that, one can observe that. When you're on the metallic side of the metal insulator transition, you've got extended states, and you can electrons can move. When you on the insulating side, you've got a Fermi glass, and nothing can move at t equals 0. But I don't do my experiments at t equals 0, so I have to be able to understand the transport at finite temperatures. And at finite temperatures, you have variable range hopping. So here's a phase diagram. It's a rather, well, I mean, not such an unusual phase diagram. Here I'm plotting the conductivity versus the temperature on a log-log plot. And you should think about, well, and disorder here is a implicit variable. If I start off with a system with a very small amount of disorder, system of the kind I've been talking about here, where I have a continuum of density of states and the Fermi level is in the middle of the band, that's a metal. Okay? So if I have very small disorder, I'm up in here somewhere. Okay? Maybe way up in here. The conductivity might be 10 to the 5th or something like that. Copper. You cool a sample of copper down to low temperatures, the conductivity gets higher and higher and higher, depending on how perfect the material is. Now I increase the disorder by putting in impurities and whatever. And of course the mean free path gets shorter, so the conductivity moves down. It's still a metallic system, so as you reduce the temperature, the conductivity would increase like that. And then finally I get to such a high level of disorder that I get into the Fermi glass regime. When I'm in the Fermi glass regime, all the states are localized, and in this case the electrical conductivity is determined by Mott variable range hopping, and as I go down in temperature, the conductivity drops to 0 in this peculiar way, 1 over t to the 1 over d plus 1. That the crossover between metal and insulator is a true phase transition. And if it's a true phase transition, there should be a critical point. There should be a critical regime. And there is, okay? And so on this diagram, the critical regime is determined by a straight line here, and precisely at the phase transition, precisely at the critical concentration of disorder, the conductivity is a power law. So this dash curve here, at that point, the conductivity versus temperature is proportional to T to the beta power law. So the conductivity in the insulator goes to zero exponentially. Conductivity in the metal stays finite at T equals 0. Right at the critical point, which separates these two, conductivity must be 0 at 0 temperature, but it has this very nice power law dependence predicted by theory. Now, for example, you might think about what would happen if you're sitting very close to the critical point and you put on pressure. What would pressure do? Pressure pushes the atoms or the molecules closer together, causes the bandwidth to be a little broader. And so pressure, I think intuitively you will agree, pressure tends to move you from insulator toward metal. And it does, and I'll show you some data. What about magnetic field? Well, you know, if you have on a magnetic field, electrons want to go around the magnetic field. So a magnetic field, in some sense, tends to localize. So, again, if your system is very close to the critical point, magnetic field can take you this direction. So it's nice. I mean, I have now, if I can somehow manage to make samples that are in this critical regime, that are very close to this critical point, maybe say slightly on the metallic side, then I can cause that metallic system to become an insulator by putting on a magnetic field. Or if I'm just on the insulating side, I could cause that insulating system, Fermi glass, to become a metal by just these subtle effects, okay? But in order to do that, you've got to be sitting right here on the metal insulator transition. So I'm back to this picture. So what I'm doing now is I'm thinking now like, say, polyaniline or something like that. I've got the a metallic system with a Fermi energy. I'm going to put more and more disorder on. The mobility edge is going to come marching down here, and eventually it's going to cross over, and then all the states at the Fermi around the Fermi energy are localized, and I've got the insulator, the Fermi glass, and variable range hopping. When the mobility edge is right on top of the Fermi energy in this picture, you're at the critical point. That's the point where you should start seeing this power law in the conductivity. So I think you can see that typically it's not very easy as an experimentalist to obtain a sample which has just right at the critical point. Now, people have done this. I mean, there's some beautiful work in silicon with impurities, and the metal insulator transition there occurs at an impurity concentration of about 10 to the 18th per unit volume. The reason for that is, as you remember, when you put, say, phosphorus in silicon, the orbit is fairly extended because the dielectric constant is large. So if you just play that game in your mind, you'll start to get space filling of all those orbits at something like 10 to the 18th. But it was a lot of work, and it's very difficult to get samples that are that right at the metal insulator transition. It just turns out that when you make polypyrrole or polyaniline or PDOT, for some magic reason that I don't really understand, samples are typically very close to the metal insulator transition. You can go more metallic, you can go more insulating, but it's rather easy to hit the precise point. So here are a set of samples of polypyrrole. In this case, the polypyrrole is doped with PF6, and the stoichiometry is approximately 1 in every 4 rings. Okay? And this, as you know, is a good conductor. And the question is it a metal, or is it a Fermi glass, or what is it? And so let's look. Oops. How will we do that? Well, let's look at the electrical conductivity. Okay. So here are a series of samples. They're all the same chemistry. They were just prepared in a slightly different way. In this particular case, all of these samples were polymerized electrochemically, and sample A was done with a very low current density, very slowly, and at a low temperature. Sample F was done at room temperature with a much higher current. And it turns out, I mean, maybe it's not so surprising, this sample is more ordered and this sample is less ordered. Here's the same plot that I had, in this phase diagram. Here's the resistivity versus temperature. The resistance goes up but remains finite. That is to say, it remains a metal. Or, in the more disordered sample, as you go down in temperature, the resistance goes up dramatically. This one clearly looks like if you extended the temperature to lower and lower and lower, it would remain constant. This one probably would remain, finite. This one already is not clear, and if you look at this curve, this point E, and you plot it log, as I have, it should be a straight line, and in fact, the slope there is about 1/3. That's the critical point. Okay? So by changing the perfection of the material with a constant number of electrons, I've gone from poor metal, not a very good metal. If it were a really good metal, then the resistance would decrease as I go down in temperature. But here it increases a little bit, not much. Starts off at, these are normalized plots, starts off at 1 and only goes up by a little bit. It's almost constant. As you put more disorder, critical point, insulator. Fermi glass insulator. A convenient way to quantify this is in terms of the resistance ratio. But here are the data, okay? This first sample, which I said was most metallic, has a room temperature conductivity of about 340. The next sample is 310, the next sample 270, the next 230. So the conductivity is decreasing. If you go back and read Mott's papers, okay, early papers, he estimated in a very, very general sort of argument that the critical conductivity, which separates metal and insulator, was about 300. Okay? Now we know now that his calculation, that estimate is not quite right, because he was thinking of a first order phase transition. He was thinking he thought at that time, he thought that the electrical conductivity as a function of the disorder, he thought the electrical conductivity would drop to 0, okay, like a first order phase transition. He called this value the minimum conductivity for metallic behavior. We know now that this is not a first order phase transition. Conductivity goes to 0 continuously. But nevertheless, the arguments that Mott made, the magnitudes are generally correct, and this goes back basically to the conclusion that KFL has to be approximately 1 if you're going to be near the metal insulator transition. So it's very nice that you know, this is not 10 to the minus 2, and it's not 10 to the 10,000, but it's right on the region of where Mott predicted it would be. So I want to plot the resistance at low temperatures divided by the resistance at room temperature. Okay? And of course, that ratio, that resistance ratio here is about 1.7. You can see that. And here it's already 9, and up here it's about 100. Okay? And I've plotted those, I've listed those numbers here. This is the resistance ratio from 4 degrees Kelvin to room temperature. 1.7, 2.5, 2.8, 160. This is the, this one was the critical point. So in some sense, this is like, roughly, like an order parameter. Okay? This is telling me where I am on this phase diagram. If this resistance ratio is very large, then I'm in the insulating regime. If this resistance ratio is 1, I'm in the metallic regime. And if I get into the regime where the mean free path is many lattice constants, the resistance will decrease, and so this would be 0.1 or even 0.01 or even 10 to the minus 3 in a very good metal. Okay? So the resistance ratio tells me where I am relative to the metal insulator transition, and metal insulator transition happens here, you know, when that resistance ratio is approximately is in this range of a few. So let's look at the reflectance. The reflectance, as you know, is a very good way to characterize a metal or characterize a conductor. And in a metal, the reflectance, we talked about this the other day, versus the frequency, has this nice feature of a plasma edge, and reflectance comes up and goes to 1 at 0 frequency. If you talk about a system which is same number of electrons but is a poorer metal, that is to say the conductivity is lower, then you tend to get a series of curves like this. This falls off more rapidly, okay? Because when the conductivity is very high, the limiting behavior drops off like this. So this would be an infinite conductor. There's this mathematical machine called the Kramers-Kronig relations. And if I give you the real part of the dielectric constant, you can put it into the Kramers-Kronig mathematical machine, and out comes the imaginary part. If I put in the real part of the conductivity, you know. So now what I want to do is take these data, and I want to analyze them, and I can, using the Kramers-Kronig response to response functions or transformation to obtain the sigma of omega and epsilon of omega. Okay, so but let's talk about sigma of omega first. So here's the here are the data that come for those 5 samples from those reflectance curves. Okay, now what do you expect? Well, let's go back to what we know about simple metals. Okay, and in the last part of the 19th century, Drude worked out the frequency-dependent conductivity, and you know the answer. For a simple metal, the frequency-dependent conductivity goes like some constant over 1 plus omega squared tau squared, where this constant is Ne squared tau over m. Okay, which is, well, that's a Lorentzian. Okay, falls off like 1 over omega squared tau squared. So on a picture like this, you'd expect a Lorentzian to kind of look like that, right? Starts off at some constant value and drops down like 1 over omega squared tau squared. Now, disorder, that's only true for the perfect system. Here I have systems which are approaching the metal insulator transition. So instead of getting just the very simple Drude model, which you would expect for truly a metal, Mott and Moshkava modified the Drude theory, including disorder. Okay? And what they found when they did that was that the frequency-dependent conductivity is the Drude conductivity, looking like this, modified by disorder in this way. Okay? And you notice that in this correction term, there is the famous KFL, which is the quantity that Yoffe and Regel used to define the boundary between the metal and the insulator. This term here, as you can see, goes away as the frequency goes to 0. So at 0 frequency, this conductivity is the Drude conductivity times 1 minus some constant over KFL. Now, right at the critical point, this constant is such that conductivity is 0. As you go above the, in the insulating regime, C goes to 1 over, it goes to 1 times KFL squared. So if you take data of this kind, you can fit these equations. And 0 frequency resistivity, you get this constant, and you get KFL determines the shape. This is the most metallic, this is the next, this is the critical point, this is the more insulating. And what you find when you analyze these data, first just look at it, right? So this one is coming down, but still remains finite. And here's the conductivity at 0 frequency. As you get more and more insulating, the conductivity goes to 0 because it's an insulator. And when you do the fit, you get KFL, and it's just remarkable. KFL is 1 for the same sample that gives you the power law. So at the critical point where you see the power law, you get 1.01.